So this is chapter 7 for soil dynamics at BiT-CEng 7141. So following the previous chapters, this is where we see what additional loads we have for our earthquake resistant design of foundations. In the chapter 6, we have seen it for slopes and retaining structures. So this will try to see the remaining shallow and deep foundations. And similar to the static analysis and design, during seismic loads, you'll have some additional load because of some inertial and kinematic activities. So there are mainly two ways: a pseudo-static approach and then a fully software analysis or equivalent linear analysis using Plaxis or FLAC or other geotechnical softwares to get additional earthquake and seismic loads. Once you get the seismic loads, the design, how you find your section, concrete sections, how you design it for shear and bending moment is very similar to what you have done in the past for static analysis. So really what we see here is just try to see the methods, either a pseudostatic approach or a software approach, how we can get the seismic forces, approximate seismic forces, or equivalent for equivalent design. So we'll look at those. So content-wise, we'll see some introduction case histories, some foundation failures. We have seen some of this in the introduction portion of the course, but we'll repeat them because they are very applicable for this section. And we'll quickly review the static bearing capacity of soil, and then we'll see it how it's extended to for dynamic approach for seismic bearing capacity for shallow foundations. And we'll see seismic loads on shallow foundations and deep foundations. And there is also approximation where people use a soil spring modeling approach for foundation soil. So normally, because of limitations of softwares modeling the entire soil and structure, in some cases, it's acceptable to represent the soil by springs. But it's preferable to model it as is, but we have lots of simulations. Nowadays, the commercially available software like Plaxis, FLAC, they have limitation doing that. So what we usually do is geotechnical engineers, we approximate the structure and we fully model the geotechnical portion. And the reverse is true for structural engineers. They approximate the soil with soil springs. And then they fully model the structure and analyze it. So we'll see those approaches, how you can find it. Once you have, the strain-dependent properties, the damping, and the GG curves, you can see really, find the soil springs. So from dynamic soil properties, what we have seen in chapter 5, you can use those to come up with the soil spring, equivalent soil spring. So many foundation failures have been recurred in the past caused by earthquakes. Failure in foundation can be due to various reasons such as sliding, overturning of structure due to lateral pressures, damage caused by excessive soil amplification, such as resonance, or liquefaction-related damage, such as the Niigata earthquake, Japan. So usually it's the ground because seismic comes from the ground, and the way the ground is what affects the structure. You can have so many things, tilting, falling, or liquefying, anything. And we have seen it also like a resonance case in Mexico City earthquake. We'll review quickly those because those are foundation failures. And we'll try to come up with some kind of solution so that in the future we don't have similar kind of failure. In order to protect catastrophic damage on foundations and buildings, detailed geotechnical investigation needs to be performed to identify the kind of foundation to be used for a specific site depending on geological conditions and economical considerations. And in some cases, we may even avoid sites for any kind of construction. if it doesn't make sense economically. So case history one, Mexico City building foundation damaged by excessive soil amplification. We have seen this in chapter one and probably more times in other chapters, but this is a very good example what can happen due to resonance. You know, the entire city of Mexico, it's built on a loose clay sediment. It used to be a lake in the past. So what happened is this is loose deposit, and we have seen amplification, seismic wave propagation. You're familiar, like impedance ratios. So what comes earthquake in the bedrock? This is the bedrock, and this is the soil portion. So the soil is loose deposit, and the rock is there. So some earthquake comes, but what happens is it gets amplified through that soil. Now there is a critical amplification where you can find the fundamental frequency of a soil deposit using this relation. For now, just assume you know what Vs is, which is a shear wave velocity of the soil, divided by 4, divided by h is the depth. So we'll derive this equation in chapter 9. But for now, assume you can calculate the fundamental frequency of the soil with this Vs by 4h approximately. And for depths around 40 meter, and for shear wave velocity of that site, it's around 80 meter per second. It's a loose soil deposit, loose clay deposit, and it's approximately about 80 meter per second. And fundamental frequency is around 0.5 hertz, period is around 2 seconds. Now, you're familiar with the resonance. We covered it in detail in chapter 2, right? So if you have a motion comes and this deposit amplified it, and it has a period around 2 seconds. We're considering approximately 40 meter, but there is fundamental frequency at any depth. But just in average, we're considering 40 meter because the depth increases. So what happened is for a period around 2 seconds, that's where 2 seconds is, around here. Normally, the Mexico building code, they were designing it for this horizontal lines. You see it. That's what they were expected to design. The blue line was in 2017, and the magenta line is a pre-1985 code prediction. This is what they predict at different years. So let's see the 1985 earthquake. That was the more catastrophic earthquake. So 1985, they expected around how much? This is probably 0.25. They were expecting 0.25 spectral acceleration. And buildings are designed for that. And this is what's recorded. This is the building code. That's what it's telling them. And this is what is in the rock. This dot lines, the magenta line, this one you can see it. It's a rock, UNAM, and surface. Surface is this one. It's a rock, and rock is right here, like outcrop and under soil. But when it amplifies at the top of the soil, that's what happens. See the two magentas, this compared to this. So what happened? What happened, Michelle? Resonance happened. The soil resonated. The soil resonated. And what was expected around this, around 0.04 or 0.1-ish G, it's around 2 seconds. What they get is around 0.9. So in 1985, there was about 12 times of amplification by soil. So any building around this, so imagine, and it closely matching the resonance within this range, even up to 3 seconds. This area, it's severely exposed to seismic forces, this area. It's not only the peak. Anything significantly larger than the design. The design is right here, right? The design is this value. This is the design. Anything above this, from around point 1.5 to 3 second, those buildings are subject to much larger accelerations. So buildings in Mexico City, they were those buildings. I mean, building frequency. It's complicated. You cannot really see the height of a building and see what's the fundamental period. It depends on the framing. If you have larger sections for beams and columns and shear walls, it may affect it. So there may be building which didn't collapse even with a height of around 10 story. But those buildings which have a period around 2 seconds, from 1.5 to 3 seconds, they were catastrophically damaged. Very tall buildings with very high period, very short buildings, they were not affected that much. So scientists, researchers, they didn't have, this kind of understanding in those days in 1985. But after this damage, then people realize, okay, what's affecting is the soil underneath. So you can't really build with a shallow foundations in this case. You better go deep down and use piles to the bedrock. Or you can simply change the stiffness and shift the period of the structure. And instead of being within this range, maybe you can shift it. If you shift it, which means very tall buildings with a high period, they are around here, right? So they are not affected. The seismic force acting on them is less than 0.2 G. But a shorter structure, a stiffer structure, which is around 2 seconds, 0.9 G. You get the idea, right? So even by just doing a geotechnical investigation, by doing boreholes, by doing seismic wave propagation tests, by understanding what's underneath, where the bedrock layer is, if it is inclined, you do those wave propagations both ways, and understand what is the VS of the soil layer, what's the VS of the rock, everything, you can make a judgment what kind of building to be built in that site before anything starts, just at the project initiation phase. So this is the job of the geotechnical engineer. You can save lives and a lot of money by just doing this simple thing. And your recommendation for foundation type. If somebody asks you, would you go with isolated footing or mat or deep foundation? You can tell. Deep foundation is much better. So you want to avoid too much dependency on the soil. Or you should recommend very tall buildings, or shift the period somehow. Do not stay within this range. If you have to stay, what you should do? You should design it properly, right? You should be able to resist maybe more reinforcement so that beams and columns don't crack and fail. So this is a very critical step at the initiation of the project, and it's mainly dependent on geotechnical engineers. As a geotechnical engineer, as a geotechnical earthquake engineer, you make that decision way ahead of time before anything starts. So you understand what response, that's why we studied what response spectrum is, how you put everything. Well, that's why we studied wave propagation techniques, to understand the dynamic properties of soil. Once you have the dynamic properties of soil, you can easily find fundamental frequency of the soil and the period of the soil. Now you can discuss. You may not have good understanding about the structure, the period, or so much detail about the structure, but you can discuss with the structural engineer. We usually work together, right? Because it's a big project, it's usually everybody involved. Geologist, geotechnical engineer, seismologist, seismic engineer, and structural engineer. Everybody work together. Then this is your input to the structural engineer. Hey, I have this kind of soil, and I may have a resonance, so I'm not recommending this type of buildings in this site. If we have to do it, then let's make sure structural engineer will give you the period, fundamental period or fundamental frequency of the structure. It's easy to determine it. Once you have a software model, they can do a fixed base or a spring base analysis and get the fundamental period of that building. Softwares can give you easily, Start Pro, SAP 2000, easy. Once you have that, now compare it with the soil. Are you close within the resonance range? If you are close, then you know, which means it's not, you may not say, hey, you cannot build it. The point is, if you build it, don't design it for around 0.2 G. Design it for this, 1 G. If you apply 1 G in that building, it should be able to resist it. Is that clear? So this is a big concept. Now you can understand pretty much everything after going through theory of vibrations and dynamic soil properties and what resonance is. Now it should be clear for you. This is the purpose why we covered the previous topics. In the introduction, I just gave you, okay, there is this amplification, that amplification. And at the beginning, you were not clear even what response spectrum was. You were not clear what VS, this fundamental frequency, everything. Now it should be clear. This is the first analysis you do. Once you understand your soil from your test, lab test, or geophysical investigations, you should expect some amplification. See how the rock motion is amplified. See how the energy content is wide. That's because of soil. So this is purely amplification. So these are the damages in those buildings which were not designed properly. They were completely overturned. And see the tall buildings, the high periods. See the high period, see what acceleration you are acting on. The high periods, let's say around 4 seconds, see it's very low acceleration. Or it's about the design, this area, around 0.25 G. So pretty much nothing happened. Maybe a few cracks, window cracks, things like that, but no collapse at all. Mexico City collapsed buildings in 1985, blue symbols. See how many buildings collapsed. This is the model prepared after the earthquake. And in 2017, red symbols. 2017 also a few buildings collapsed. At least I see here 4 or 5. On the contour map of the soil zoning and vibration period. So we looked at the 1985, but after 1985, the code improved. So engineers in Mexico, they got together, they got some advisors maybe from other countries. And in 2017, they improved the code after 1985 and see now what they are recommending. They are recommending to design it at least 4.4. They raised it from 0.25 to 0.4. And then another earthquake happened in 2017. That blue one, this is the rock motion. And with that earthquake, still it's exceeded, but not as big as in 1985. The blue line exceeded. Now it's a narrow range. So anything from 1.5 to 2 second period, still it's affected. Few buildings, but still, that's why you see few buildings collapsed, the red ones. The other case history is liquefaction and sand boil during the 1964 Niigata earthquake. So what happened here in Japan is you have a loose deposit, a loose sand, saturated sand. This is a loose saturated sand. The water table is right here. And for loose sand, usually what happens is the particles are loose. So now when you have a seismic shaking happens there, what happens is the particles try to get compacted. They go down. And during those, what happens is it's compressing the water within the voids. It's so fast, the shaking is so fast that the water doesn't have enough time to go up. So we're compressing the water here. And we create artificially high water pressure. The water doesn't have enough time to escape. So this happens usually in granular soils like loose sand. It settles so fast, try to compact so fast, and it compresses the water and artificially creates high water pressure. And that high water pressure is sufficient enough to cause like go up through here. You see it here. The water pressure is going escaping like a fountain. And with it, it takes a sand deposit with it. And once you have this, what happened? There is some instabilities happening. What this is causing is the whole thing is now turning into a liquid. The sediment particles are going down, like here. It was a compressed water. Now you have something semi-liquefied soil. You design it assuming that you are dependent on the bearing capacity of the soil. Now you don't have it. What you have is the soil already lost its shear capacity. It turned it into semi-liquid. And buildings tilt, can even collapse. And this is what you have. You can see it. So initially you have this sand, we call it sand boil. Water is escaping out because it has high pressure, being compressed by the sand particles. Now see what happened on the ground. You see this? Initially the ground was right here. My pointer is not correctly showing on my laptop and on that screen. So you see it right here is the initial water table. And because the particles settle and because the water is going up, now there is some void space. We are having some settlement. The whole ground is going down. You see it, initial and the final one. And some instability in between. It's a complex dynamic phenomenon. But the major takeaway is high water pressure is created in that loose sand deposit, and that high water pressure escaped through, we call it sand boil, and then it causes semi-liquid sand, and now buildings are unstable. These are sample sand boils happening in the field during the earthquake. Sand boil, sand volcano during 1964 Niigata earthquake. And you see some examples of buildings tilting and falling and cars swallowed because of that liquefied nature. It's like liquid now, it's not a solid ground. Structures collapsing, piles tilting, bending and breaking, and so much. So this is a complex phenomenon. And it usually happens in loose sand. It doesn't happen that much like in clay soil. In clay, the particles don't try to settle fast. Because that cohesive nature, they are contact to each other. Even if you have shaking, it's very little going down. But sand, as soon as you shake it, compacts faster. So loose sand is the most dangerous for liquefaction susceptibility. So if you geotechnical investigation, either through using a soil lab test or geophysical testing, if you see a loose sand, and if it is a seismic area, if there are faults around, that's a pretty clear sign that you may have a potential liquefaction at some point. So you see how the geotechnical engineer is making the big decisions. If you have a liquefiable soil, now you should be very careful what kind of structure you are recommending, what kind of foundation you're recommending. So either we should remediate the soil to avoid liquefaction, or use something like a deep foundation. We'll see detail what kind of recommendation you'll provide. Different stage of loading and failure mechanism of pile foundation during earthquake. Even if you have, if you are not dependent on the soil, let's say you have a loose sand. And loose sand, you say, oh, I may have liquefaction, so I'm not going to do any, shallow foundation. Especially isolated foundation is the worst one. Mat is better. At least the whole thing can, survive together. But differential assessment-wise, the isolated foundation is the worst one. Or even piles which are in shallow depths. let's say you may have rock and you can put, your pile foundation socketed to the rock. So even if this soil liquefies, you may assume, hey, I may not have any issue. But still, you may have. A loose sand, you have inertial forces. There are two kinds of forces. We'll see it in detail later, but you have kinematic interaction and inertial interaction. Inertial is because of the mass of the structure at the top. When you have seismic acceleration acting on the mass, you have inertial forces. Kinematic is because of the soil. Because the soil is also moving, the soil somehow laterally applies force on the pile. So you have inertial and kinematic forces. So now let's consider only the inertial case. You have inertial force. Initially, let's say you have soil liquefies. Now you have inertial force. So the pile is subject to high bending moment and shear. Assuming this is liquefied, assuming this is liquid now. You lose that skin friction, and also you lose the lateral support from the soil. So you can have, a liquefied sand and high bending moment and shear at the bottom of the pile foundation, or where it is located with the rock. Or in some cases, so you should design it. When you design this, ignore the soil entirely. That's what it means. Do not be dependent on the soil. Assume the soil will be liquid at some point. So when you design, the shear and the moment for the pile, that's what you have to consider. Assuming the worst case, you don't have any soil. If it turns into liquid, at least the pile will survive. Or in some cases, you may use like a diagonal pass, bracing, not only vertical. So in some cases, you may have a sloping ground. If you have a sloping ground, it's even worse. Because once this liquefies, what's happening to this slope? It's going down entirely. The soil is actually now applying a huge load on the pile. So it's not only inertial load at the top from the structure. If you get, the peak ground acceleration A and mass times the weight of the structure, at least mass times acceleration will give you some inertial force. But now see what you have underneath. You may have a case of lateral spreading or the entire thing, moving. So the soil is also applying on the pile. It may not entirely liquefy, but a little bit is enough for the slope to fail. So there is so much complicated going on. So here you have only gravity static case, then seismic case with no liquefaction. If you don't have liquefaction, you may be able to use a support from the soil. Seismic case with liquefying in level ground. You can have liquefaction in level ground with liquefaction, so you can design this. But if it's a slopy ground, you can have now lateral spreading. Even the pile being subject to weight of the soil behind it and seismic forces. So you should carefully, conservatively design it that way. Pile foundation failure in liquefiable soil can be by bending and or buckling due to axial loads. Pile is now like a column. So if you have a column, it can fail by so many things because you can have complex loading, axial loading, moment, and like lateral load. It can fail by buckling, can fail by breaking at the base, high bending moment. Buckling is usually axial load impact. And together with lateral loads, it's very critical in that case. So documented history of pile foundation failure during earthquake. There are so many pile failures recorded in the past. You can go through this link or see this table. So many things reported in the past. And in some cases, you can see figure A. This is what they observed. After the damage, they go deeper up to 80 meters the piles, but usually it's shallow failures and even around the rock where they are because it's liquefied, and even at the top area breaking. And liquefied zone, if you have a liquefied zone, it breaks in both plates, depending on the layer of soil you have. This may be where it is socketed. And liquefaction zone, you have this, both side breaking. This is building in Niigata city during Niigata earthquake A and B. And C is buckling in Kobe city, buckling due to the axial loading, combined with the lateral loading. So you can go to the detail of these case histories. I put the link here. You can search it and freely available online. Collapse of Showa Bridge, Niigata earthquake due to pile foundation failure. Now we know how piles can fail, but the collapse of this bridge, the entire bridge, it was attributed to especially these two pile failures. Right here you can see the pile bent. See, the pile failed here, then the deck failed. Then it's a chain reaction. The deck starts failing everywhere nearby. If your foundation structure may be fine, but once your foundation fail, like such as something lateral spreading, this is under the water. Then the deck failed, and then when you see the building at the top, the bridge at the top, that's how it failed. Generally, cracks on walls and floors or wall and door windows deformation after an earthquake are good indications of foundation damage, either by sliding, overturning, differential settlement, or a combination of these failures. So usually, engineers do survey after an earthquake. When the Indonesia earthquake, the 2004, 2005 occurred, I was in India. It caused tsunami and it caused so many building damage. And all our professors from the earthquake engineering department, they left for survey. And they came back. And what they do is really looking for indications, trying to understand what happened. So next time, what we should do. After an earthquake, even before an earthquake, if you see building cracks like this, what does it mean? Even in a static case. This is showing you there is something wrong in the foundation, like a differential settlement. Once the foundation settle, then the bricks at the top, they don't have any support. So you see those cracks. So if you do building inspection now and if you see cracks, either there is a loading issue or there is a foundation issue. These bricks, they are usually not load bearing. But if there is a foundation issue at the base, then what you can see, these are good indicators. So let's quickly review. Those are about the case histories, examples. It gives you a good understanding of what earthquake can do, and it increases your understanding so that you know what you expect in your design. There is a lot of judgment, a lot of survey, field investigation, lab investigation, so much to be put on before you make a decision for designing building, before you go to detailed design or computer analysis like that. So let's see the bearing capacity of soil. We'll start from the static, from what you know from your undergrad or foundation design class. And the bearing capacity in the dynamic case is a direct extension of the static case. So researchers have developed for seismic condition. So let's review of static bearing capacity of foundation. Terzaghi and Merov, you have three components: the cohesion component, surcharge component, and granular soil component or friction angle component. So the ultimate bearing capacity can be given by cohesive times the bearing capacity factors, depth factor, shape factors, and so many factors. You're familiar with these factors, so I'm not going to go deeper. So in this, they are assuming a failure surface, like this, the active wedge, the passive wedge, for general CFE soil. So the idea is if you apply a load in the static case, the way the soil fails is it's sliding through this surface, and you may see some bulging around here finally if it fails by bearing capacity, while this portion with the load portion is going down. And you have these bearing capacity factors. in relation to the angle of internal friction of the soil. Up to from 0, our normal soil is probably somewhere in the 20s and 30s, but you have any relation from 0 to very strong rock up to 50. Maybe rock is anywhere from 45 or from 40, depending on how stiff the rock is. But you have this relation for bearing capacity factors. So this is the same as from your undergrad or from advanced foundation design for graduate class. For seismic bearing capacity of foundation, it's very similar, except now they approximated, with a straight line instead of a curved failure, what you have there in Terzaghi and Merov. Now they assume a straight line sweeping surface. You have some depths for surcharge factor. Otherwise, it's pretty much the same for CFE soil. So the failure would be, let's say, if you don't have this surcharge, then we're talking is slipping through here, foundation down for axial load. And the loading may be complicated. In seismic case, it's not axial load only. You can have bending and shear. So we're considering the vertical load right now, but we'll come to the lateral load. It causes sliding together with settlement. And the bending moment, it causes what? Tilting. If you have high bending moment here, you can have tilting of the foundation. So in seismic case, it's more complicated, but we'll see one by one. So we have similar researchers developed bearing capacity factors for some cases for quadrilla soils, at least for a static case. If you have this equivalent equation for seismic case, now the main difference is in the bearing capacity factors. Now for the static case, NQ and gamma, now we will have a QE to say earthquake, seismic case. They're modifying those. It's very similar to the dynamic earth pressure. When we go from the static to the mononopio method, they incorporated seismic acceleration and they used pseudo-static analysis. Here also is also a direct extension. Very similar extension, except now we are modifying the bearing capacity factors. And the seismic coefficients come right here, the horizontal and the vertical. And we may use effective friction angle. In this case, you can use a reduced friction angle. We talked about that conventional method where it uses 20% reduction at least. Even people use a reduced value conservatively for a static case. Alpha A and alpha B inclination angle for active and passive pressure waves. This is the static case, and this is the dynamic extension. Wherever you see E, that's the earthquake extension. So similarly, this is the factors they develop, researchers develop. Static bearing capacity factors, the one we saw on big table, from 0 to 40. NQ and gamma for static case. Now for the dynamic case, seismic bearing capacities. I might have missed to say E here. These are E. NQ and gamma E. I'll fix that one. So you can see it. For example, at 20, NQ is 6.4 and it's 5.9 for seismic case. Or N gamma is 5.39, it's 6.4 seismic case. And it doesn't mean that it will decrease or increase generally. You may see it decreasing for low phi values, but it increases, especially the N gamma, you see it 22.4, 23.8, 109, 112. So it doesn't mean like, it will reduce. Depends on the soil type, the phi angle, but there are more factors to see. But this is the equivalent values for pseudostatic bearing capacity of a soil. So for a static case, if you have soil friction angle phi, you can get the NQ and N gamma, for example. Those are the plots or the data we have seen, NQ and gamma. You can find it like this. For 30, for example, you can find it around here. then N gamma is larger, it can be like this. Now, NQ, this is a chart provided for the seismic case. So if you see the ratio of bearing capacity ratios, N gamma E by N gamma. This is a static value. You can find it here for seismic cases. N gamma is, you have solid line, the dashed line is NQ. And depending on the seismic coefficient ratio, KH by 1 minus KV, that's a seismic coefficient ratio. Depending on where you are, you can find the seismic bearing capacities. So this is just a same relation as the table, but it gives you more complete. If you have the data, you can use it, but if you don't have it, the figure would provide you everything. Especially, if it changes from site to site depending on the acceleration values, this is the better to use. Because the seismic coefficients can vary. Settlement of strip footing due to an earthquake. So the bearing capacity for a strip footing was developed like that from researchers. This was developed long time ago, 1980s, 70s. But nowadays, we have much better sophisticated tools. We have softwares to help us. This is what they used to do in the past. They understood, the seismic behavior of soil is different during a seismic than static condition, and they started developing these tools. They didn't have a fully finite element simulations in those days. So this is what they have been using. Nowadays, you may not have to use this. Just model the software and run it. And provide a correct seismic value, seismic soil strain compatible properties, or constitutive models. If you use constitutive models, you have full nonlinear analysis, but equivalent linear properties like degradation curves give you a faster solution, but it's also like a pseudo-static approach. So settlement also in the past, Richard and Elms, they developed in 1993. So they developed the seismic settlement for a strip footing. They used the peak ground velocity, peak ground acceleration, the acceleration value, seismic coefficients, and they provided a factor of safety, static factor of safety versus KH. You have input to come from here. And they developed the KH, the seismic coefficients, with effective friction angle variations. And so you can get the settlement of, this is an approximate, just empirical equation if you have to use it. It doesn't mean that it's widely used right now. In US, I never use this equation. We usually use software nowadays because we have better tools and they are available. So we estimate settlements using, Plaxis. You can model it in Plaxis and see what the settlement is. This is for a strip footing only, right? How about if you have mat or other foundations? So there is limitation in the applicability of this equation also. And it uses constant acceleration. So of course the dynamic property of the soil may be included. But it's not as accurate as when it's compared to, dynamic analysis. But you have it. If you have to use it, and just know what they were developed in 1993, this is what they have been developing and using it. Just to give you an example, example 6.3 from reference 2, a strip foundation is to be constructed on sandy soil with width of 1.2 meter, depth of foundation 0.9 meter, unit weight of soil 17.6 kilonewton per meter cube, and effective friction angle 30 degree. Determine the gross ultimate bearing capacity, QUA, which is seismic case, total case. Assume that the seismic coefficient, the vertical is how much? 0, it's ignored. And the horizontal seismic, which is, usually the horizontal is the more damaging one. So you don't see it being ignored. It's larger in magnitude and the shaking is lateral. is very critical. KH is 0.176. If the designer's parameters are V 0.4, this is the PGV, peak ground velocity. We have seen that in chapter 4, right? And A is 0.32, determine the seismic settlement of the foundation. Use factor of safety of 3 to obtain the static allowable bearing capacity. So this is just to show you what we have seen in the previous 2 slides and how you put it into, reality. So from 6 to 10 for phi is equal to 30 degrees, you can estimate the static bearing capacities. 6 to 10, I provided you here, I believe. Yeah, this one. For 30, you can estimate the corresponding values, NQ and N gamma. Somewhere around a little above 20 and a little below 20. 16.51 and 23.76. Phi, the seismic coefficient factor, you can estimate it. The vertical coefficient is 0, KH is 0.176, 0.176. For tan theta equals 0.176, figure 611. That's the seismic bearing capacity factors. This one is with respect to this parameter. Depending on where you are, you can find the ratio of the seismic bearing capacity factors by the static capacity factors. N gamma E by N gamma 0.4, NQE by NQ 0.63. So since you have N gamma and NQ, you can find really the seismic bearing capacities. So QE, the ultimate bearing capacity, now you can find it. This is your surcharge unit weight by depth of foundation. NQE, you have it. Half gamma, beta, and gamma A, you have it. So 265.06 kilopascal. I don't think we have it. It would have been a good exercise to include the static portion only, because this is a total one. If you do the static portion only, you should find it different from here. So this is the settlement portion. You can go to the same exercise. I already provide you the graphs, but you can practice and see how you do the settlement and the bearing capacity for this case. You can run the numbers and get your settlement. Section 7.4, seismic loads on shallow foundations. It's complicated loading, right? You can have a vertical loading, like a water tank here. Last time we estimated the bending moment on a water tank using a response spectrum. I was trying to show you how you pick a response spectrum acceleration and use that to find forces and at the bottom of at the top of the foundation. You can have a mat foundation or a pile and pile caps like that. But we were studying there to see how you pick accelerations, how you compute period of that structure. The period of this structure may not be easy. Simplified equations from Roark's formula, you may not find it for complicated like this. Simply regular shapes, rectangular shapes, circular shapes, or hollow, you may find that one easily. But something like this, you may have to use softwares to model it. If you model this in software, in SAP or StatPro, you can find what period, fundamental period it has. That is the most significant period. Because the mode of vibration, it may be more complicated, maybe like this. Usually we focus on the first mode, we call it the fundamental mode. The peak or the fundamental mode here, the rest, what we do is, what did we do last time? To account for other modes, other peaks. You remember multimode factors? We multiplied what we get by 1.5. We pick acceleration from the response spectrum corresponding to the period of that structure. Then we use the multiplying factor of 1.5 to account for higher modes. because there are other peaks. Even though the biggest one is at the fundamental frequency, there are other modes, second mode, third mode, mode of vibrations. But they are smaller. But to account for those, we increased it by 50%. That's acceptable in conventional design. If you're doing, a quick pseudostatic analysis, like by hand, like a hand calculation. So you can easily calculate, what we did there is we came up with the acceleration, we multiplied by 1.5, and so we know the acceleration acting at the top. And then we use that weight and acceleration. So because of horizontal force now, mass times acceleration, using that, we came up with bending moments and shear force at the bottom. That's what we did. It's good. It's quick. It's conservative. I mean, if you do a time history analysis, the force is less because multiplying it by 1.5 here and picking this peak value, it's very conservative. There is a penalty out of it. Your design would be a little bit uneconomical. More reinforcement needed. More sections needed. But to give you a quick analysis. Otherwise, the more realistic is model the whole thing. Anyway, you're modeling it to estimate the period, right? So run that using the full response spectrum or a time history. If you do that, your forces at the bottom, they will be less. But you have more tasks to do. Modeling, simulation, it may take a week or more than that, depending on the complexity of your structure. So any structure you can have. Now, this is the lateral load, and we get the moment. And also we have a vertical load, right? And we have a moment on the other side. So we have biaxial moments at least. Biaxial, by shear, two lateral shears, in the X, in the Y direction, and a vertical load. So it gets a little bit more complicated. We're approaching it, very easy, from the easy one to understand than to the more complex one. So footing under vertical, horizontal, and moment loads can be considered as one of the following. Now, if you convert, let's say, the previous slide, using response spectrum, you pick your acceleration. Now you found your axial force, lateral force, and moment. I'm sure you studied something eccentric loading in your undergrad foundation class or in advanced foundation class. You consider eccentric loading, right? That's very similar to seismic. In a static case, usually, we may have the load really at the CG. And forget this moment now. So the load distribution is uniform. But when you have some eccentricity, what it means is, it means like you have some moment. A moment with axial load, you can really represent it like some load at eccentric distance. This is equivalent. These two are equivalent. Even if you come up with some moment at the base for that foundation, what it means is basically this axial load is acting at some eccentric distance, E. So you can move this equivalent load Q at E, like you can take the whole Q axial load right here, but it comes with some moment, right? So the two are equivalent. So what you have studied actually in eccentric loading is applicable for seismic case. The only difference is now you should incorporate the seismic forces, because that moment you get is using the seismic loads, the acceleration, the corresponding acceleration. So now your E is from seismic too. The rest is the same. What you do, the load distribution you have because it creates some inclination in the foundation, or the distribution is not uniform. You may have a maximum bearing capacity, maximum bearing stress here, and minimum bearing stress here. Depending on the magnitude of that moment and the eccentricity, this may even be zero. Q minimum can be zero. Or it can even create separation, right? Maybe even like this. So what you studied in the eccentric loading, because seismic causes eccentric loading in the air. Because that shaking, when you see the building shaking like this, it's causing eccentric loading. So you can design it properly like that. This is a pseudo-static approach. You are using it as a single acceleration, conservative acceleration, convert it into a force, and then get your moment, and then get your eccentricity, then follow the static case. The bearing stress, you have a vertical load by area plus by a moment. The moment by section modulus is the other stress because of eccentricity. If you don't have eccentricity, this guy is how much? Mahadar. If I don't have eccentricity, if the load is really vertical only, then the second component, this, do I have this? Zero. You don't have it. That's what usually happens in static loading. If we design it properly to be symmetric and the load is at the CG and everything. But when seismic comes, that's not the case. Even if it is like that for a static case, now you have eccentric loading because of lateral shaking. You have additional moment acting. So Q by A, M by S is section modulus. Section modulus, assuming rectangular section, you can calculate it like this. Assuming there is a 1 meter width we are considering, you can calculate S is by I by Y for that rectangular section. Y is usually extreme fiber distance from center to the edge. Y is B by 2. I for rectangular section is 1 B square, assuming this is 1. 1 B cubed by 12 and B by 2, so B squared by 6 is your section modulus. So you can simplify this equation. It can be plus or minus. The plus is the max one, the minus is the small one, the Q minimum. So depending on this, you can have separation. We call it even separation, right? So you can have a foundation really, during the shaking, it's moving sideways. But it may not be observable, but the stresses vary right here. It may not be visible how it moves for the eye, but if you have a computer model, you can really magnify and see it. So you can have different cases. You can see it for E, eccentricity less than or equal to the width by 6 corona. You can have, even this case, some bearing stress minimum and maximum, or you can have it in 0 for eccentricity if it's equal to B by 6. Or if eccentricity is greater than the width by 6, you can have even separation. You can have a Q max. This is the same of what you did in the eccentric loading of foundation. But the difference is what? Eccentricity, even if you have it like in eccentric case for a static case, it will be more for the dynamic case. Your eccentricity is larger because you have that lateral load from seismic, which causes more moment. Methodology-wise, like a pseudo-static approach, you can follow the same. In May of 1953, recommend concept of effective weights to calculate the bearing capacity of foundation under eccentric loading. This is same as the static case. The effective weight is B minus 2E. This is one way we are looking at it. We are looking just one direction now. We have moment in the other direction, right? Also, so it can be in the you have to design it in the other side too. So even if we see this stress just in this plane, you have to also see it the other side. So in the end, the effective width may be this much only, not even this full. So horizontal seismic case, that was for vertical seismic and moment, but horizontal case, it can cause also what? You have a shear force, right? We don't have only axial and moment at the foundation. At the foundation level, if there is seismic, we have also horizontal forces, right? Here we looked at only what? Here we looked at only moment and vertical force. How about the lateral force? So it can cause what? It can cause sliding. Now that lateral force, it can cause like the lateral earth pressure. If you don't have enough support, you can have sliding. The only thing resisting that lateral seismic force is friction and soil passive pressure the other side. Otherwise, this entire thing, like a PA, it's moving, it's applying it. So the slab can slide, foundation can slide. So it needs to be properly embedded. And there are factors of safety to be computed. So this is where you consider the effect of the horizontal seismic force. You can go through this write-up and understand more. Section 7.5 seismic loads on deep foundations. We can do this maybe tomorrow. And I'll send you this slide.